Hello. In today's video we're going to look at Chapter 16, Lecture 13, the first learning objective, identifying and defining acids as either Arrhenius, Bronsted, and we'll also look at Lewis, and then we'll look at what's hydronium. So first let's go over what an acid and a base is. So acids themselves, you are probably familiar with some acids, such as citric acid. So these are going to be substances that have a sour taste. Some of them you would not want to taste, but they will have a sour taste. They are going to be substances that neutralize bases. And then some other things about them. They are going to dissolve or react with metals. I'll be in this following reaction. Our M plus our HA, which is how we represent our acid, produces Ma plus H2, so there's a 2 here. So we'll produce a salt and hydrogen gas. We call this a single replacement reaction. It'll also turn litmus paper red. And it is a corrosive substance. Okay. Then we have bases. These are going to be bitter tasting. Generally, you don't taste bases quite as much, but if you've ever had baking soda, for instance, it has a very bitter taste. It neutralizes acids. It's going to turn red litmus paper blue. It is also going to be corrosive. And then it's going to be slippery to the touch. And it's slippery because the base itself is turning the fats or oils on your hand into soap. So you're actually feeling soap being produced when you touch a base. With acids and bases, we are going to bring back the idea of equilibrium. So an acid-base equilibrium is an equilibrium between an acid and its conjugate base. We'll look at the idea of an acid conjugate base series. So we have an acid reacting with water, equilibrium between that right there. So that'd be an equilibrium process, and this occurs when this is a weak acid. Okay. If we have a strong acid, we will not have an equilibrium process. So instead of a two-way arrow for equilibrium, and we will identify weak acids versus strong acids. We have the same idea when we have a base. So we have a base equilibrium. So BOH. With our equilibrium itself, we're going to have B plus H2O is an equilibrium with BH plus OH minus. But if we have a strong, so this would be a weak base, a strong base will just completely dissociate will not be an equilibrium process. So we're going to look at the differences between strong and weak acids, strong and weak bases. Weak acids and weak bases have our equilibrium. Strong acids and strong bases are a one-way reaction where it goes from reactants to products during its dissociation. Okay, so let's look at our different definitions. For acids and bases, we can be an Arrhenius acid or an Arrhenius base. With an Arrhenius acid, this is a substance that increases the H plus concentration or H3O plus concentration in water. A base is a substance, or specifically an Arrhenius base is a substance that increases the hydroxide concentration in water. Both of these, notice these are both specifically in water. If we have a Bronsted-Lowry acid, this is a substance that donates H plus ions or protons. And then a base, Bronsted-Lowry base is a substance that accepts protons. Okay, and then our last definition is the Lewis acid Lewis base. A Lewis acid is a substance that accepts a pair of electrons. Well, a Lewis base is a substance that donates a pair of electrons. So each one of these definitions, they're named after the person who came up with it. Arrhenius is the same Arrhenius that came up with the Arrhenius equation. Bronsted and Lowry were two gentlemen that came up with the idea of protons moving between substances, and Lewis is the same guy who did Lewis structures. Okay, let's look at each one of these more in detail. I'm going to look at Lewis in a different video because it's a little bit, like a whole lecture for that one. But we're going to look at Arrhenius and Bronsted a little bit more in detail. So if we have an acid, it's going to give off H plus in solution, or according to Arrhenius. So an acid is a substance that releases H plus ions in solution, or in water. So if we have our acid, it's going to release our H plus ions. So when it does so, it's going to increase this concentration. Okay, and this can be either a strong acid or a weak acid. But in either case, it will increase our H plus ion concentration. Okay. A base, on the other hand, in the Arrhenius definition, gives off hydroxide in solution, or produces hydroxide. So we can either look at a strong acid, or sorry, a strong base. When it dissociates, we produce hydroxide ions, or in the case of a weak base, it will actually react with water to produce our hydroxide ions. Okay. So, the problem with Arrhenius is that when we use the Arrhenius definition, we don't produce salts that have acidic or basic natures, because salts will not usually cause the production of H plus or OH minus, but they still can, in fact, be acidic or basic, and we'll look at that a little bit later on. And another issue with the Arrhenius definition is an acid or base is only an acid or base if we have it in water, which is not true. So let's look at a more inclusive definition, the Bronsted-Lowry bases. So Bronsted-Lowry bases and acids are going to basically move protons between them. So an acid donates a proton. So we can have something like HCl producing proton like so, or something like NH4 plus. So both of these would be considered a Bronsted-Lowry acid based on the fact that they donate a proton. With the base, it accepts a proton. So we can have something like sodium hydroxide. So it's H plus, so it's going to accept that proton, producing sodium ions and water. Or we can have something like NH3. Actually, this would be equilibrium process. So in both these cases, we are accepting a proton, so we've considered a Bronsted-Lowry base. Now, in these two right here, I've shown H plus ions as this independent thing that's just in solution, but that's not actually how that works. H plus ions are unstable in solution. So they will actually latch on to whatever they can, and generally we're talking about a aqueous solution. So when H plus ions are released from an acid, they're going to be taken up by water. Producing hydronium. So if we have an H plus ion in water, we'll produce hydronium like so. So we would say that H plus ions and hydronium ions are interchangeable in an aqueous solution. So you could talk about the idea of hydronium ions or hydrogen ions or protons. Those are all interchangeable terms. Okay, so let's look a little bit more at our Bronsted-Lowry acids and bases. Let's look at some options or some things that are considered acids. So acids can be neutral, so no charge, such as HCl. So HCl, we take that and we put it in water. It's going to donate that proton to water, and we're going to produce hydronium. And chlorine ions. Okay. We can also have Bronsted-Lowry acids that are anionic in nature. So HPO4 2 minus. Actually, I'm going to do a slightly different one. HO4 1 minus. Plus water will give us hydronium. And our SO4 2 minus anion. And then, of course, we can have a cationic species. So something like NH4 plus. But in general, with all of these, we're going to have a general formula. HA plus water. And of course, we don't have to react it with water. We can react it with anything that is more basic. And if it's strong, it's going to have one-way arrow, or if weak, a equilibrium area if it's a weak acid. For our bases, this is going to be a substance that's going to be capable of accepting a proton. So we can have a neutral form or an anion form. So neutral there, we can have an anion. Something like that, or we just transfer the proton, or something a little bit more exciting. Like so. So again, we have a general formula, which would be B plus H2O goes to BH plus OH minus And we can also look at it from the anion form. A minus plus H2O goes to HA plus OH minus. So, lots of different ways of looking at it. Okay, so let's see if we can classify each substance as an acid or a base, and then what we will do within within water. So the first one right here, we have a positive charge. That's going to indicate to us that this is going to be an acid. Okay, so we have NH4 plus water gives us NH3 plus hydronium. Okay, HNO3, because of that hydrogen right there, and there's no charge, so if you see a hydrogen with no charge, you're talking about an acid again. So HNO3, nitric acid, when it reacts with water, nitric acid is considered a strong acid, so it's going to be a one-way arrow, giving us NO3 minus plus hydronium. Here we have a hydroxide that's going to indicate to us that this is a base. So KOH with water will produce K plus ions plus hydroxide ions plus water, so it doesn't actually interact with the water at all, it just breaks apart. And that's how any strong base will behave. It'll just break apart and not actually interact with water. Calcium hydroxide, it's a hydroxide again, so we know it's a base. So CaOH2 plus water will just break down. Ca2 plus 2OH minus plus water. And then the last one, we see that hydrogen right there, so we know that it is an acid. So we have HCl plus water. HCl is considered a strong acid, one-way arrow. Like so. Okay, that's everything for this one. Bye, y'all.